Yeah, perfect. Thank you very much. And thank you to the organisers for inviting me. So this is some work that we've been doing at Newcastle. Hopefully it complements Raoul's talk. The bulk of this work has been done by Gary Liu, the postdoc on the project. There's Carlo, who many of you will know, and Toby Wood, who's got a background in neutron star physics. So I put a few introductory slides in. I didn't know if there'd be PhD students. It looks in the audience like maybe these aren't needed, but anyway, as many of you will know, British people like talking about British weather, and particularly like complaining about British weather. And so I took this opportunity to do so. But really all I'm wanting to display here is a classical velocity field. So here we can see some storm that's come from the Atlantic, this region of low pressure, and this large vortical region. And obviously the point that I'm trying to make is that this vortex, the size of it, the strength of it, is not constrained. It's constrained by the system size and the available energy. But this could be larger. Only we complain about this, but this is not a hurricane, okay? Whereas if we move, okay, I'm making the same point again. So we can have vortices of all different sizes, from galaxies down to storms in a teacup, and all different strengths. But if we move and put this through this quantum black box, so this is actually the team of Camerlingers and the first liquefaction of helium, then we see quantization of circulation and the appearance of quantized vortices, which here are visualized in the helium experiment with these hydrogen deuterium particles. Okay, so from there, let's move to neutron stars, and this is a very famous image from the Hubble telescope, and this is the Crab Nebula that was first observed, we think, by Chinese astronomers in the 11th century, and then rediscovered by a British astronomer in the 19th century. And this image, many of you will have seen before. It's one of the most famous images from Hubble. What you might not have seen is this secondary image, which zooms into the heart of the Crab Nebula and shows the pulsar that was left behind through the supernova explosion that created the Crab Nebula that these Chinese astronomers saw. And a little bit on neutron stars, so Raoul touched on some of this, but I'll also flesh this out a bit further. So they represent the sort of end stage, or the sort of reincarnation of massive stars, stars much larger than our own sun, which undergo these supernova explosions. Here there's a numerical simulation of one taking place. And what's left behind at the center of this, you can sort of see in this image here, this is actually a numerical simulation of a magnetar, an incredibly magnetized neutron star. But it had the prettiest picture. And what we get at the heart of this object is intense gravitational collapse. And it's energetically favorable for protons to capture electrons and leave, as Rahul said, this object that's just completely packed with neutrons. And these are incredible objects. They're city-sized, in the order of kilometers, but of the order of a solar mass or two solar masses. And what's particularly interesting from the point of view of this workshop is that even though they're very warm, there might be billions of Kelvin, on the sort of scales of nuclear energy, these are very, very cold systems. Or put another way, they're orders of magnitude colder than the Fermi temperature. So things in them have either got to be solid or superfluid. We know when we cool things down, they're the only two things that we can get. So they're very cold, very dense objects. And as Raoul pointed out, we know about them because many of these stars have very intense magnetic fields, and they radiate electromagnetic radiation from their magnetic poles. And if there's an offset between the rotation axis and the magnetic axis, you get these cones swept out like a lighthouse that we observe on Earth as these very regular periodic pulses, leading to the name pulsating stars or pulsars. Now, if we look inside these stars, this is a system that's very far away from what we can recreate in laboratories on Earth. We're typically complete opposite end. If we're doing high energy physics in particle accelerators, we've got very, very hot, very, very low density, This is cold, very, very high density. So we don't have an equation of state for this, but we have a canonical picture of what the interior of a neutron star will look like. We have rough ideas for what the radii of these particular layers will be. And the region that I'm going to be interested in is away from where there is both a neutron superfluid and a proton superconductor, but in this outer crust in this inner crust region where we've got a superfluid and some impurities that form these pinning sites that Rahul mentioned. But we'll get to them shortly. So these, I think this might be even the same figure that was in the last talk, where we see the rotation period of the star. And in that previous slide where we saw this electromagnetic radiation being emitted, there's obviously a transfer of angular momentum away from the star as it radiates, and this causes the star to spin down. And so we see the rotation period drop, and then every now and again, this rapid speed up, and then some longer term relaxation back to this regular spin down. We see this in many of these pulsar objects. There's one here, another one here, and then this is a much more recent observation where this really captures just either side of the so-called glitch, where we see this rapid spin up. So the statistical distribution of these glitches, they're characterized by power laws, exponential waiting times, as was pointed out in the previous talk. And so what that brings to mind is this classic sandpile model of avalanches. So if we think in terms of dynamical systems, the fixed point of this system is a critical state, and we get these avalanches that occur every now and again as we pile the sand on this object. And what we want to try and do is capture this in a superfluid system using the Grospa-Tierski equation. So let's talk a little bit more about the structure of this inner crust and how it motivates our modeling. So in the outer crust itself, we have a normal fluid, we have a crystalline lattice, and as we move further in to that outer crust, we get more and more neutrons present in the nuclei. And then eventually we get to a depth where it's energetically favorable for these neutrons to drip out and form a neutron gas that sits between these lattice sites. And this is shown by these calculations here. Here we see the neutron density, maybe this one's easier to see. We see the neutron density here and the proton density. And so we have these regular clusters of protons and neutrons, and then between them, a neutron gas that we think is a superfluid. And so what we want to do is model this through the Grospa-Tierski equation with a periodic potential of pinning sites that mimics these neutron-proton clusters. So we also have a very simple picture, a cartoon picture for how these glitches might occur. So we have this crystalline outer crust that rotates rigidly at this observed rotation rate that we see in the electromagnetic radiation. And this inner crust and the superfluid itself is some sort of reservoir of angular momentum that is coupled to the crust in a complex way. And it acts as a store of angular momentum, and eventually we reach some out of equilibrium state where there's some large-scale depinning of lots of quantized vortices. They release angular momentum and transfer this very, very rapidly to the crust, causing this object to spin up and giving a glitch. And there's been a whole host of activity in performing, in the main, numerical simulations using the Grospa-Tierski equation in 2 dimensions and 3 dimensions in a rotating frame with a complex potential of lattice pinning sites or other ways of putting the pin in. And it's the 2D ones that I'll focus on because that's the work that we'll do as well. But there's also 3D work, as discussed in the previous talk. There's other 3D work. In terms of 2D work, the one that I really want to focus on, I think was a paper that was pointed out by Rahul, was one of the few papers in 2 dimensions that simulated a large number of vortices. And Large is sort of rather tongue-in-cheek because they get up to sort of 200 vortices, and we won't really go that much further. Whereas when you look at these large-scale glitches in something like the Velar pulsar, they involve an incredible number of vortices, far beyond what we're ever going to be able to simulate. What we'd like to do is start to see some indication of collective behavior in the vortices, so that we might start to extrapolate to these larger scales, even if that's a little bit of a leap of faith, given the sort of scale separation. So let's talk through what they did, just to set the scene for what we'll do afterwards. So the vast majority of their paper focused on smaller scale numerical simulations. So these are shown here. There's a small number of vortices, and what they vary as we move down this plot here is the strength of the pinning potential. So this pinning potential, I'll talk about in a little bit more detail when we get into our work, but it's essentially a periodic lattice of Gaussian pinning sites. And the strength of that pinning is parameterized through this V0 parameter. So here there are no pinning sites effectively. As we move down, you start to see these pinning sites, and it's hard to visualize in grayscale. There's always this background lattice of quantized vortices that sits on this pinning potential. And then slowly the system is ramped down. They model the crust and make some assumptions about what the moment of inertia is, and slowly, effectively, the rotation rate of the system is ramped down. And what they see are these glitches, these jumps, that are particularly prevalent as they increase the pinning potential. So when there's no pinning, we see this smooth ramp down of the rotation rate. As the pinning potential is increased, it becomes jumpier and jumpier. What they would hope, I suppose, is glitchier and glitchier, and that some of these large-scale features are similar to what we see in a neutron star. I think the problem is that when you've got such a small number of vortices, actually these jumps really are just associated with a single vortex leaving the system. And so it's hard to sort of tie that up with this picture of collective motion or collective behavior and 10 to the 10 or 10 to the 13 vortices doing something collectively. So what they do is quite natural. They scale this up and say, if we move to more of a continuum, if we move to hundreds of vortices, do we see this thing amplified? And what they see is just before we get there, what they also looked at, and this will be important when we get to our own work, is they looked at varying effectively the electromagnetic braking. So they varied the spin down rate. And as you spin down slower, what you see are fewer glitches, but they're a little bit larger. And this will be important, like I say, when we get to what we do. Now what they do is go to these larger scale simulations with hundreds of vortices. So I think something like 200 vortices here. And again, there is this periodic pinning potential, and everything is done the same. It's ramped down. And what you see is what we feared that we might see in our work, is that when you move to more of a continuum system, these glitches really get washed out. One vortex leaving the system, when you've got 200, really, you don't notice this unless you really, really zoom in and try to make some arguments that this very, very minor jump in the angular momentum of the crust is really a glitch. So that sort of sets the scene for state of the art in 2 dimensions. There was some follow-up work where they looked at more complicated pinning landscapes. And another open question that came from a slightly later paper is, what's the mechanism that leads to these vortices depinning? Is there a Magnus force effect? Is there an acoustic effect where large amplitude sound waves can knock vortices off these pinning sites? Or could there be some interaction if the vortices get very, very close, that their cores overlap and there's changes to the density, that can pop a vortex off its pinning site? And so we wanted effectively to answer 2 questions. If we move to these larger scale simulations comparable to the later part of that paper that I just showed you, can we actually find something that looks glitchy? And can we start to understand what's the mechanism that drives the unpinning of these vortices? And hopefully in the next 20 minutes or so, we can make some steps. So what we did was, before we went to the large scale simulations with this complex pinning potential and many vortices, we asked a really, really sort of simple question, almost trivial question of what's the critical velocity for a single vortex to be depinned? And can we sort of estimate that using energetic arguments? So we have a very simple setup. It's a homogeneous domain. It's periodic, and we'll get to that in a second. And we put a single vortex in one of these Gaussian pinning sites, and we progressively ramp up some imposed background flow and see what flow is required to pop this vortex out of this pinning potential and free it, and it can then move away with the flow. As I mentioned, to do this, we use a periodic system, and so that comes with a few issues that we have these vortices to maintain periodic boundary conditions. So we play a few little numerical tricks. I won't go too much into them. They're mentioned in this paper on the archive if you're interested. But at the boundaries, we have large values of gamma. We have this sort of buffer zone so that any edge effects are hopefully mitigated by that. And what we find is the following picture. So you can easily work out what the Magnus force is in this system. And these are simulations for progressively larger imposed velocities. And what you see is this vortex moves to the side with the Magnus force. And eventually, when this is large enough, it can pop out of this pinning potential and then move away with the flow. What we also see when this happens is the emission of sound as this vortex leaves the pinning site. What we then do is just make some simple energetic arguments. We can compute what the energy of a free vortex is, what the energy of a pin vortex is for different imposed velocity fields. And what we see is what you might expect. As we increase the imposed velocity field, it becomes more energetically favorable for a vortex to be free compared to be a vortex to be pinned. And what we can do based on energetic grams is look at where these two curves overlap and say this is the sort of velocity that we would think that a vortex would be depinned. What we actually observe in the simulation is this dashed gray line, which is slightly higher, but maybe that's associated with this additional energy that's required to create this sound wave as well when depinning. But this gives us a criteria that we can use for later in our simulations. Because if vortices become depinned when the Magnus force is larger than this, then it's that mechanism that's depinning them. If we measure the local Magnus force at a vortex, and it's very, very low, but we see that vortex depin, it must either be acoustic effects if that vortex is isolated, or if another vortex becomes very, very close, it's this core overlapping picture. Okay, so now let's move to our large-scale modeling. And again, we're in the framework of the Gross-Pitievsky equation. It looks fairly like what Rahul did. It's not self-gravitating, but we have some background rotation, and we have a fairly complex potential that's made up of three terms. So there's a confining potential, so we're not self-gravitating. So we confine with a hard wall cylindrical trap. We have this pinning potential that I'll talk about in a second. And because we're rotating this system, the centrifugal force would mean that our density isn't constant. To counteract that, we add an additional potential, which is effectively an anti-centrifugal potential, which means that the density across the domain is effectively constant. The background density field, that is. And then we have this lattice of pinning sites, which are these Gaussian potentials, whose strength we can control by this V0, and whose width we essentially fix to the healing length. And I'll not spend too much time on this because it doesn't look very good, but it shows you how far away we are from the real system. So I think it's fair to say we are not modeling a neutron star. We're modeling a superfluid system with some complex pinning landscape and trying to see if some of the features that we see in neutron stars are also present in our system, because, as you see, some of the parameters we might be reasonably close, but in terms of size of the system, the rotation rate, we're not in the same ballpark. Okay, so this is what we simulate. So we have this reasonably large domain, and we have about 1,500 lattice sites, and how many vortices? About 650 vortices. So it's a little bit larger than that simulation by Ballarini, but it's the same order of magnitude. We solve using a pseudospectral method that I won't really go into too many details. We propagate in imaginary time and find the ground state of the system, which is this slightly strange lattice that emerges with many of the vortices sat on pinning sites, but some of them actually free and not on pinning sites. And so it's obviously energetically favorable for not all the vortices to be pinned. And in some early simulations, we essentially found very, very similar results to that paper by Wozowski and Ballarini, where as we spun the system down, if we compute the angular momentum, it essentially looks like a smooth curve without any of these jumps. You might say there's one here, but it's very, very small. And you might be able to see it, I appreciate it's very, very small, but these are the rotation rates that were picked, and just like the earlier work of Wozowski and Ballarini, as we slowed down this spin down rate, it did become a little bit more jumpy. And so we just took this to the logical conclusion. We could perform longer simulations with the sort of increases in computational efficiency. Before we get there, we can start to see what the system looks like. So what we're plotting here are vortex trajectories. We're varying the strength of the pinning potential here. They all essentially look very similar, so it doesn't really matter. And we're plotting the trajectories of just vortices that are free and moving, and they're colored as a function of time. And what you see is there is this interesting localization in space. So even though the lattice is periodic, we form these preferential rivers or tributaries that the vortices tend to want to move through as they leave the system. But there's no localization in time. These all start at roughly the same time and move out, which perhaps explains why our angular momentum curve doesn't show these large jumps that we might hope to see. So then we really slowed the rotation rate down by an order of magnitude again. And what we started to see was the system did become more glitchy. That's the verb that we want to use. So if we compute the angular momentum, or we just look at the number of vortices in the system, we see it becomes much more step-like. Now, we've not included a crust in our calculations, primarily because we just have no idea what to put for the moment of inertia. But if we infer these large drops in the angular momentum of the superfluid system has been transferred to the crust, however it does so, then these large drops will correspond to these spin-ups that are observed. What's perhaps more interesting is that when we look at these same trajectories, we recompute the trajectories of free vortices in the system, and again plot them as a function of time, we see there's not only a localization in space, but also a localization in time. And it's that gives rise to each of these events. So you can see the first one starts here, collectively a large number of vortices, order 10. It's not large, but it's more than one, move out of the system, and as they leave the system, obviously they take the angular momentum away with them. And then each of these corresponding drops are associated with more of these events occurring. So we start to see some evidence of self-organization in the system and some collective effect, where one vortex depinning can trigger multiple other vortices in the vicinity to also depin and all leave the system, leading to something like a glitch. I'll now play a movie of this, and there's quite a lot going on here. Pin vortices are plotted as these open markers. Free vortices are plotted as solid red dots, and this background glow that you can see is a coarse-grained vorticity. So we effectively apply some Gaussian blur, or it's a cubic spline that we actually do, to compute a vorticity if we smear the vortices out over a couple of intervortex spacings. If you're sort of interested in the details, I can talk more about that over coffee. But where lots of vortices see the system, we're going to see a void in that vorticity field, is the main idea. So remember, the first event is coming at sort of 9 o'clock. And so what we tend to see are these voids in vorticity occurring near the edge. There's 5, 10 vortices leave the system, and then they propagate back, and there's some large-scale motion induced by this void in the vorticity that is something like a post-glitch relaxation, where vortices can reach some new equilibrium state, which then becomes unstable as we continue to ramp down that background rotation rate. I'll not play it for too much longer. It's the same sort of thing. Each of these events looks very similar. Now what we can do is plot the same thing, effectively, but there's a little bit more going on here, that we're going to color the vortices according to their effectively local Magnus force. So it's the vortex velocity with the background rotation rate subtracted off, and it's normalized by that critical Magnus force that we found from a single vortex. So where vortices start to become red is where this quantity is becoming larger than what we think is required for the vortices to depin. Now there's a bit of a caveat, because obviously that simulation and those energetic arguments are based on a single vortex. And here there is the influence of lots of the vortices that might stabilize. But what we see is that it's when this quantity approaches 1 that we start to see these events. Remember, the first one is at roughly 9 o'clock. As the background rotation rate is dropping, this frustration in the lattice is building. This Magnus force is increasing, so our points move from blue to red. And we start to see vortices here now that are exceeding that threshold, and then they start to move out of the system. And as they do, they induce this void in the vorticity field, which propagates backwards and then induces more vortices to depin. So we see this collective behavior, which we think is the hallmark of one of these glitches in the real system, albeit we're a long way away from that in terms of the physics that's included in our model. And if a movie's too difficult to see, then these are just some snapshots, which basically are showing the same sort of thing, but they're trajectories that are colored by time, and the vortices are colored by this quantity. Sorry, let me get my head around this plot. So in these figures here, the vortices are colored by this quantity. It uses a slightly different color scheme, apologies. But where the vortices are blue is where we think they should start to depin. And then we're plotting the trajectories, and the coloring is purely through time. So we see one vortex leave the system, and that starts to trigger multiple other vortices to leave the system. And that creates the void, so this is a slightly later time. That creates this void that can then free more vortices, and they can rearrange within the lattice. And what we started to do, I appreciate I'm running out of time a little bit, what we started to do is try to quantify how collective this motion is. So there's a whole other field of physics where people are interested in trying to understand flocking, collective motion in biological systems and human systems in terms of stampedes. And what we've done is borrowed a couple of tools or a couple of measures from this community to try to quantify the collective motion of the vortices in our system. And the idea is effectively to look, I appreciate this is slightly complex and I'm running out of time, but if we have a vortex here that's free, then we look at all the other vortices within some radius r, and we compute a couple of quantities. One of them is a sort of average velocity of all the vortices within that radius, and one is some sort of velocity correlation. And what we expect is, if the vortices are moving collectively, this measure should move from 0, which would be random, completely uncorrelated motion, to 1, giving a sign of collective motion. And what we see is, if we look at these events, so plotted here is the angular momentum of the system, plotted here are two measures for collective motion, and the y-axis here is the radius of the interaction. So it takes a little bit of time to get your head around this, and there's probably not the time here. But essentially, where we see these colored bursts gives some indication that the vortices at that point are moving collectively. There's some correlation to their motion, and the radius over which this extends, so the depth of this, gives some indication of the length scale over which this motion is collective. And that sort of corresponds roughly to what you see when you look by eye. And if you color the vortices, no, sorry, that's not what's plotted here. This again is just more trajectories of the vortices as they leave the system. So I'll finish there, and hopefully I'm still sticking to time. So I think the takeaway points are that we can see something that looks like an avalanche in this system if we go to very, very slow spin down rates in the presence of this complex pinning potential. What's sort of core to seeing that is a localization of the motion of vortices both in space but also in time. Order of vortex motion occurs both during these events and in this post-glitch relaxation, if we can call it that. And we can quantify this order using measures from the field of collective motion. So one parameter, if I do have time to go back to my table of parameters where we're wildly off, and points at an obvious next step, is these numbers here are the distance between vortices in the lattice, and this is the distance between pinning sites. And in our simulation, these are effectively the same. Whereas what you see in a real system, in a neutron star, what we estimate at least, is that the separation between vortices is incredibly large. You know, it could be close to 10 orders of magnitude compared to the separation between pinning sites. So we're a long, long way from that. And so an obvious next step is to try to move towards a regime where there is either fewer vortices in the system or ideally a much larger density of pinning sites, if that's feasible. And then the next natural step is to move this system to 2D. Sorry, to 3D. Okay, and that's where I'll finish. So I pinched these slides from Gary, the postdoc who worked on the project, and writing these slides had obviously made him hungry, and this structure of the neutron star had made him think of the ambassador's favorite chocolates. So I'll leave it with that. And thanks very much.
Okay, thank you, Andrew.
So do I need to look at Zoom or? Yes, yeah.
Why do you choose a rectangular lattice that would be not like something natural packing? And that geometry of that lattice to a triangular lattice that is more towards what will you get different, obviously different quantitative results, sorry, quantitative, but could you actually get different quantitative results in the avalanches of getting that underpinning lattice that is more conducive because of lattice?
Yeah, I mean, I guess we don't know what the lattice structure really is. We think it's some ionic lattice, and so this regular periodic lattice is a sort of simple thing to pick. Early on, we actually picked a random lattice, just because it was maybe slightly easier to implement. When we saw the emergence of these tributaries, if you want to call them that, or these preferred paths, I think there was a bit of a concern that perhaps we were seeing them because of a Poisson random process, that there might be some sort of percolation. There are regions where it's easier for the vortices to penetrate, and so it was the background random lattice that was giving rise to this focusing in particular regions. And so that's why we moved to a periodic lattice where if we saw this focusing into distinct regions of space, it's nothing to do with the lattice, it's actually the vortices themselves. But we've not looked at other regular lattice structures that might be more realistic. And certainly if you move to 3 dimensions, obviously the options for lattice design increase as well. So yeah, it's an open and interesting question.
So you may be far away from astrophysical objects and so on, but I'm sure you're aware of the experiment of Tzakade and Tzakade in the 80s, I think, where they had an experiment where they had a spherical experiment rotating, and they observed these glitches, and maybe you can compare better to them.
Was this the superconducting experiment?
No, it's superfluid helium rotating in a sphere.
Yeah, okay, yeah. No, I'm not aware, so it's worth...
I'll show you.
Yeah, thanks.
Thank you for a very nice talk. These defects, there really should be the proton vortex, proton flux tubes. Is that right? Proton superconductor flux tubes in the eventual...
Well, not in the inner crust, where we're away from where we think the protons are superconducting.
I see. So these are just bare protons.
Yeah, we've avoided that complication by just focusing on a region where we think there's just a pure superfluid.
Quick question, and then maybe the rest we take it over coffee. Yeah.
Okay, so thank you, Andrew, for the nice talk. My question is, in your talk, so you seem to indicate that your pinning sites have a characteristic length scale that's of the order of the healing length. And for small number of vortices, I mean, of course, when you unpin one vortex, it carries a significant fraction of the overall angular momentum, so you see a glitch. When you have a large number and you just unpin one, it doesn't have much of an effect, so everything seems to be smoothed out. So I was wondering, I mean, wouldn't another way to get glitches for a large number of vortices would be to actually change the characteristic length scale of the pinning site make it larger when you have a large number of vortices to continue to see glitches, because there's no reason it should be of that scale under the real system.
Yeah, I mean, I can't remember what the estimates are for the actual size of the pinning sites in terms of the vortex core. What really motivated the size of our pinning sites is that parameter that I mentioned. If I can go back. We're conscious that, particularly if we're talking to people in the neutron star community, this parameter of the ratio of, sorry, I've lost my cursor, of this ratio effectively between separation between pinning sites and separation between vortices, we're a long way off anyway. We suddenly start making these pinning sites larger, that problem gets even worse. So, right, really, from the sort of modeling point of view here, we want the pinning sites as small as possible that can still pin a vortex, really. But I appreciate, yeah, it could be that there's another way of looking at it.
So let's thank Andrew once again for the talk, and we postpone the other questions